So strictly speaking, our molecular orbital theory does something like this when it looks at the p orbitals. So we can look at how the p orbitals overlap, and they can overlap in a favorable interaction or a not favorable interaction, and they generate new orbitals. And everybody kind of goes, well, I don't understand what bonding versus anti-bonding means. Okay? Really all it means is that when I bring two things near each other, they have two possible options. They can either interact or not interact. It's a little bit more than not interact. It is actively not interacting. Because on their own, they're floating around and they're not interacting as well. Okay? So our bonding is they come together, they interact in a favorable place where they're like, yeah, let's chill, let's hang out. Okay? Not interacting, it's just random people just walking around. Okay? Kind of similar to you guys just in the classroom, because you guys aren't talking with each other yet. Okay? And then you'll start to realize you can get help from each other, and you'll now have that strong interaction. Maybe in that interaction, you're like, I really don't like the way that person describes things. Okay? Maybe that's why you've stopped attending class and you're watching the video. That was a joke. There we go. Okay? That was too much pity. So we have that favorable interaction where we actually have a strong interaction. We also have the option of not interacting at all, but that was before they even got to a position where they could interact. And then we have the active, I am avoiding making contact. Okay? So there's really three situations that we can get out of sort of molecular orbitals. We get a bonding interaction. We get not involved in bonding at all, which didn't show up in this one, but that would be our non-bonding electrons. And then we get anti-bonding. Okay? And this concept, well, what is anti-bonding? Anti-bonding is really just a way of saying that there is another probability state. Because remember, all of our orbitals are probabilities. Okay? We have the probability of finding an electron in that location. When I bring two orbitals near each other, they generate two new orbitals. One of those orbitals happens to be where they're interacting in a favorable way. One of them happens to be where they're interacting in a disfavorable way. They're both new states. They're both new probabilities. So I have to draw them. I have to represent them. One of those new probabilities says that the electrons are now located between the atoms. So we would refer to that as a bond. We have electrons between the atoms. Okay. The other possible state was the electrons actively avoiding being between the atoms. Okay. So this isn't not a bond because there's an intent, if you will. The electrons are intentionally avoiding that space. So I can't call it not a bond. So we invent a new term. That new term we use as antibond. So the antibond is the actively not making a bond. Okay? The bonding is actively making a bond. It's just saying there's two possibilities that come out of it. Okay? Because one of them is lower in energy, when we populate that orbital, we expect to see a bonding interaction because it's lower in energy. What if we add enough electrons that we populate the anti-bonding?
Higher energy.
Becomes higher energy. Becomes higher in energy than the atoms on their own, which means, should the atoms stay interacting? No, and what ends up happening? Bonds break. Okay? So we can use molecular orbital theory and the electrons that we're putting into these to explain, yes, I now have a bond, or no, I don't have a bond. Okay? It's a very useful predictive ability. Okay? It does involve lots of calculations if we're actually going to quantify it, but it can also, at a superficial level, help us understand what's happening at the molecular level, and we can then start to draw predictions from it. Okay? So let's go backwards. No, backwards. Sorry, I'm trying to find the picture I wanted. And it is clearly not backwards. So we need to go forwards. Okay. One direction's not right, we just go the other way. Sorry, that takes a little bit longer. That's the picture I wanted. Sigma, there's our pi. And just because we might as well. happen to hear that. Now we'll move forward. That's the picture I wanted. It was the very next slide. Look at that. Right. We could now take this information and scale it out to our larger molecules. So in this case, what we've got drawn is ethylene. Right? And you'll notice some interesting features here, because what we're trying to draw is the molecular orbital diagram. And within the molecular orbital diagram, that means we take our atomic orbitals. Okay? S and P, those are the only atomic orbitals we have. And yet, do we have s orbitals in this diagram? Yes, good answer. Where's the s orbital? It's the red ones, which are hydrogen. So we do have s orbitals showing up in this diagram, but those s orbitals are only applying to hydrogen. Well, doesn't carbon as an atom have s orbitals? Where'd they go? We're now crossing over our two theories. We had hybridization as one distinct theory, and then we had molecular orbital theory as one distinct theory, and we said they don't touch each other. We actually bring them into each other to bring into a situation where we can interpret and better understand what's happening. Okay? As Ming was pointing out, what happened to the s orbital of our carbons? It was hybridized. How do you know it was hybridized? What color was the S? Red. Do we see any red? No. What color was the p orbital? Blue. What happens when I mix a little bit of red with a little bit of blue? I make purple. Do I have purple bonds in this structure? Yeah. Believe it or not, I just now observed that. Okay. Textbook was being intelligent with their color blending. Okay. By mixing the s and the p orbital of our carbon, we generate a new orbital. Okay. The purple orbital. That is our sp2. How do we know it was sp2 hybridized? Okay. Whoa. So in theory, what Ming just did here was recognize what the structure looked like. And then when we focus on our center carbon, we have 3 electron groups, which would be sp2 hybridized. Okay. How else could he have done that? Does anybody look at that blobby thing and say, oh yeah, it's totally just 3 electron groups? Okay, no, I agree. I don't see 3 electron groups. How many hybrid orbitals are there?
3.
So, and that becomes a tricky question, because maybe you start saying all the hybrid orbitals in the whole molecule. We don't care about the whole molecule, we just care about a single carbon. There happens to be 1, 2, 3. When do we have 3 hybrid orbitals? sp2. Okay? So we have a variety of ways that we can pull that information out. What is the bond geometry or bond angle of an sp2 carbon? 120, or trigonal planar. This drawing is attempting to show that. Okay? Notice that front one, that's really useful, Mike. This one here, okay, the one I've circled in blue there, is kind of overlapping or in front of the one back there. They're drawing a spatial representation. In our drawing, we could show this as a wedge and a dash. What have they done with that planar molecule? They've turned it out of the board, kind of aimed it at you. Why did they do that? What do you get access to visually if you draw it out of the plane of the board like that? Okay. If we look at just how it's drawn now, the Lewis structure up top, those are all solid lines, which means they're all drawn in the plane of the board. That carbon was sp2 hybridized, right? What is unhybridized? A p orbital. Where is that p orbital? I need to draw that p orbital. It is perpendicular to the plane of the atoms. Okay? So if I were to draw that, it might look something like this. I think I just heard someone say, what the hell is that? Yeah, exactly. So what happens if we took that structure and instead of drawing it planar, we rotated it ever so slightly so the plane of the atoms are actually perpendicular to the board? That p orbital that was now aimed in and out of the board is now aimed where? Straight up and down, and now I can draw that in. Now I can see those p orbitals. Okay? It allows for a better visualization of the orbitals and a better visualization of the interactions between said orbitals. Erase everything. Okay? So I've got 12 atomic orbitals that are coming into this. Okay? And one of the things that gets a bit weird here is that I am using those hybrid orbitals. So I have a p coming from each carbon, so 2 p's. I have 3 sp2s coming from each carbon, so a total of 6 sp2s. So 6, 7, 8, 1s, 9, 10, 11, 12. 12 atomic orbitals. Those 12 atomic orbitals have to interact with each other to make molecular orbitals. Okay? And I could look at how those interactions stack. Okay? If I look at the interaction between the carbon and the hydrogen, what kind of overlap is happening there? It's a direct overlap, which we can call a sigma. Okay, we have a sigma overlap. That's happening in 5 different cases. Did I count that right? 1, 2, 3, 4, 5. I did count that. Okay, 5 different places. Okay, each of those overlaps can happen in a way that is now favorable, in which case it is dinging, lower in energy than if they didn't interact. They could have also interacted in an actively I don't like you interaction, meaning we have antibonding. So every time I bring orbitals together, I get 2 possible interactions, bonding and antibonding. So if I've got 5 types of, or 5 positions where bonds happen, or interactions, I get 5 bonding and 5 antibonding. Okay, and our 5, and I'm going to do the star, we'll even add the A for antibonding. Okay. That accounts for how many atomic orbitals? 10. Okay. How does that account for 10?
5 plus 5.
Pretty much 5 plus 5, yes. Okay. We have 12 atomic orbitals. What's left over?
The p orbitals.
The 2 p orbitals. Are p orbitals higher or lower in energy than our s-type orbitals? Higher in energy. So I would expect a p orbital interaction to be happening a little bit higher up. Okay? And if I wanted to get a little bit clever with this, ooh, yeah, right, blue. Okay. Do I have 2 p orbitals next to each other? Yes. What does that mean can happen? I can get an interaction between those, okay, where they're in the same phase. If they're in the same phase, I now have a bonding p interaction. What if they were in opposite phase? I get an anti-p interaction. That p interaction is known as the pi bond, because pi begins with p, and pi anti. The red ones that we called our sigma are bonding, which, now that I told you the answer, we called sigma, and we had the sigma star. Okay? So we end up with this kind of big system, and we can look at those interactions. Okay? If I were concerned about the reactivity of this molecule, which you will be at the end of the semester, which electrons am I going to keep my focus on to be reactive? The higher energy ones. Okay, so you'll notice that they drew some electrons in here. Well, that's a bit disingenuous. How did they get those electrons? Okay. Well, let's go through and break it down. How many electrons should be drawn in this? Okay, and we'll draw our 5 sigma molecular orbitals. They won't all be the same, but we'll show them all the same. 1, 2, 3, 4. There's our 5 sigma. Okay. I want to know where the electrons are in this molecule. Well, do I know how many electrons I started with? Do I know what atom I started with? Okay, what atom did I start with? Carbon. Do I know how many electrons carbon has? Okay, which of those electrons would we expect to be going into this? The valence electrons, which would mean 4. Each carbon brings in 4 electrons. There's 2 of them, which gets me 8 electrons. Do I have more electrons that I should be accounting for in this structure? Hydrogen has how many electrons? 1. How many of them are there? How many electrons? Which means a total of 12. Let's take our electrons and start to fill them into our orbitals. Where do we first put our electrons? Don't accept s orbital. I'll accept lower energy, known as our sigma molecular orbitals. So there's the first one. Where's the second one go? Into the next one. Next one. How many electrons have I put in? What do I do now? Start doubling. How many electrons have I put in? 10. How many electrons did I need to put in? 12. Where do those last 2 go? Snap. That's where those 2 electrons came from. If I'm now concerned about how this molecule reacts, which electrons should I take access to? Am I concerned about the electrons in the pi star orbital? Why are you saying no? Almost. Almost. You want to say it again louder, see if someone else picks up on it?
We don't have any electrons to give to that?
We don't have any electrons to give to that. Anyone want to adjust that? Why am I not concerned about the electrons in the pi star orbital? Say that again. There's no electrons there. There are literally no electrons. I don't need to worry about the electrons in the pi star orbital because there aren't any. So which electrons am I going to use to react? The highest energy electrons. Okay? Which orbital holds those highest energy electrons? Orbital? Fair enough, I can accept the P. Okay. Our P orbitals, which are being contributed by those 2 carbons, making that pi bond. So when I look at alkenes react, the electrons that are going to react are the electrons located in the pi bond, okay? Or our p orbitals. Okay? I don't worry about the pi star or the sigma star because there isn't any there. Okay? What happens if I say switch to something like acetylene? How many atomic orbitals would go into a picture of acetylene? So we looked at acetylene, C2H. Sorry, I lost track of what I was doing there. How many atomic orbitals? Why do I keep doing that? Sorry, let me draw that C in. How many carbons do we have? How many atomic orbitals does each carbon have? 4. So I have a total of 8 from the carbons and 2 each from the hydrogens. I have 10 atomic orbitals. Okay. Molecular orbitals. How many molecular orbitals do I expect to get? Can you create or destroy matter? No. Okay, you might say, well, orbitals aren't matter. Fair enough. Can you create or destroy energy? Still no on that. Okay, and we'll say orbitals are close enough to energy. Okay, which means if I start with 10 atomic orbitals, how many molecular orbitals do I get? 10. Perfect. Now to the bonding versus anti-bonding. Okay. How did I get a bonding interaction? Took 2 orbitals and I overlapped them. If I start with 2 orbitals, what do I need to end with? 2 orbitals. So if I've got a bonding interaction, what else do I have? Antibonding. Okay? So how many bonding orbitals am I going to get out of my 10 molecular orbitals? 5 bonding and 5 antibonding. When I look at all of those interactions, how many of those are going to be sigma? 1, 2, 3. Okay. So of my bonding, I will, instead of having 5 sigma, I will have 3 sigma, which then means how many anti-sigma will I have? 3. 1 for 1 match. What does that mean happens to my pi? I will end up with 2 pi and 2 anti-pi. What's that?
I was making that too.
Okay. I'm with you now. That's not that bad. I like that one.
Is pi star higher or sigma star?
Pi star, as far as we are concerned within organic chemistry, will always be lower in energy than our sigma star. Okay. When looking at strict molecular orbital theory, there are exceptions on that. We see that transition between nitrogen and oxygen. Okay. And I never remember which way it goes. Okay. Because almost everything we're working with is carbon. Our pi are sandwiched in between the sigma. Okay. So if I was now to predict what's going to be most reactive for my acetylene, it's going to be the p orbitals again, because they're the highest energy. Okay? Molecular orbital theory gives me the opportunity to look at reactivity. Okay? So here's our big summary. Okay? Bond labeling. This sigma double triple is a load of nonsense. It was crap when it was originally taught to you in general chemistry. It's crap now. Okay? There is no more single, double, triple. Okay? It is sigma and pi. Okay? Sigma is a direct overlap of orbitals. What happens if I rotate those? I don't know if I've done this analogy in class yet, but if we take 2 pens, not those 2 pens, we did a direct overlap.
Oh, that's anti-bonding right there.
And we try to do a rotation. What happens to the overlap? It stays the same. Okay? If we look at a p orbital or a pi bond, what happens? Does the overlap stay constant? No. Okay? So what does that mean for our overall molecule? The sigma bonds, rotation is irrelevant, meaning it can happen. Okay? When does it happen? When we're above absolute 0. Okay? And that may take a little time to process, which ultimately means always. Okay? Pi bonds. Okay? This is where we're getting our multi-bonds. When I kept referring to multi-bonds earlier and I kept stumbling over it and calling it pi, okay, what we're looking at is the overlap of p orbitals. This is where we get double bonds from. How do I get a double bond? It is 2 bonds. What are those 2 bonds? 1 sigma and 1 pi. Between those 2 bonds, the sigma doesn't care if we rotate, but the pi does. This means when we have a pi bond, rotation can't happen, or at least does not happen easily. Okay? Hybridization. Okay? Increased hybridization means more orbitals involved, which means higher in energy, which means less electronegativity. The electrons are getting further and further from the nucleus. Okay? That comes into play when we're trying to look at where charges fall within a molecule. Okay? So we need to be thinking of and aware of what's happening with our hybridization. Okay? So those are the big things that come out of this. You need to be able to labelize your hybrid orbitals. So you look at a structure, that carbon is sp3 hybridized. Okay? Which means it has all sigma bonds. which means every single one of those can rotate, which can now potentially make the structure look, quote unquote, different, okay? Even though it's not different. If I looked at sp2, I have a bunch of sigma bonds, I'd have 3 sigma bonds, and I have the potential for a pi. As soon as I have that pi bond, now what happens? No rotation. That changes how I interpret the structure, in particular when I compare it to other structures. Because I now have sp2, this changes the hybridization, which then changes the electronegativity, which then changes my reactivity. All of it drastically stacks. Okay, so you have to be able to look at a structure and very quickly identify hybridization and at least be thinking about the electrons that are highest in energy. The highest energy electrons are coming from our molecular orbital theory. Okay? So we will come back to it whether or not you like it. Okay? It's usually coming in the breaking and making of bonds. Okay? And then kind of a fun little question here. How do we determine where the molecular orbital density was located? We said we looked at our orbitals, we just kind of said they were symmetric, right? Bonding interaction, because we were bonding carbon to carbon, or carbon to hydrogen. But what do we know about carbon and carbon? And for that matter, carbon and hydrogen. What can you tell me about carbon? Six electrons, it's an atom. 4 valence electrons. What do you mean likes to bond with? Getting at an interesting idea on bonding.
Carbon, most, I guess, least reactive when it's bonded.
Not very reactive when it's bonded with other things. Why?
4 bonds.
Electronegativity. What is the difference between carbon and carbon as far as electronegativity? Nothing, which means the bond is nonpolar covalent. Between carbon and hydrogen? Nonpolar covalent. Which means where do the electrons go? Nowhere. They are perfectly overlapped. Exactly the way they should be. What happens if we change the molecule to, say, carbon to chlorine? Is that going to change how the electrons are going to be distributed in our molecular orbital diagram? Yeah, that's going to have a significant difference. If we're going to look at how carbon and chlorine overlap, we need to make sure we're looking at the proper bond. Okay? So to start that off, it may be useful to look at the Lewis structure. What orbitals are making the carbon-chlorine bond? And maybe to be helpful. Say it again, me. sp3. So just an sp3 orbital makes that bond. sp3 and is a good start. And sp3. Both of those atoms should be sp3 hybridized because they both have 4 electron groups. So that when we go through to look at our molecular orbital diagram, do I care about the p orbitals? No, because I'm looking at the bonding interaction between an sp3 atom and an sp3 atom. So the orbitals that I should be looking at would be an sp3 and an sp3. When those overlap, what would we expect to happen? Okay. We would expect a sigma interaction. Good start. Okay. In that interaction, where would we expect to find our electron density? Rhymes with primarily between. Also kind of sounds like that. As in, it's primarily between the 2 atoms. So we see a much larger probability density of the electrons in between. What's the issue with what I've got drawn here? Sort of. It's roughly symmetric. Would I expect the electron density to be? Yeah, if it breaks, it breaks. If I expect, would I expect the electron density to be evenly shared between the carbons and the chlorines? Why not?
Because chlorine
Chlorine's more electronegative. So how should I adjust my drawing? Okay. Maybe, and this is going to look horrible, but that way there's more over there anyway. It's close enough. Okay. Most of the electron density is located towards the chlorine, but it is still between them. Okay. What happens when they don't? When they actively don't want to interact? There will be a node between them. That node we can show with a dotted line saying there's no electrons there. Okay, in the bottom one I showed a dotted line just to show the differentiation between the two halves. Okay, but in the top we cannot have electron density there, which means we would probably end up seeing something along these lines, where the electrons are now pushing actively outwards away from each other. But notice again, what's the issue? Those two orbitals are drawn symmetrically. This is the anti-bonding orbital. This is the orbital that should not exist. Which one of those should have more electrons? This is the orbital that should not exist.
So carbon.
Carbon probably makes sense to have most of that electron density. Okay. If we were to fill in our electrons, well, carbon brings in 1, chlorine brings in 1, we have an overall bonding interaction. If I want this bond to break, what do I have to supply? Energy, sure, in the form of? Rhymes with proton. Electrons, where should those electrons go? What's that? If I dump electrons into the anti-bonding, what happens? The overall interaction now between these atoms is? Our anti-bonding is actually higher in energy than our bonding is lower than energy. Which means if I populate the anti-bonding, the overall interaction is higher in energy than the atoms, which means the atoms don't like each other and actively avoid each other, meaning no bond, a broken bond. So to get this reaction, or to get this molecule to react, I need to bring in something that supplies electrons. Okay? Those electrons are going to be supplied to which atom, the carbon or the chlorine? Which one is easiest to get electrons to in that anti-bonding situation?
Carbon.
Why the carbon?
Because it's anti.
The chlorine's still anti. I don't accept it.
Shouldn't have.
Someone started to mumble it.
Bigger cloud?
What's that?
Bigger cloud?
It's a bigger cloud. To get an interaction, what has to happen? Orbitals have to overlap. Okay? The carbon antibonding is a larger orbital. Okay? Which means I have an increased probability of getting electrons in there if I overlap with the carbon. So if I want to look at how this bond is going to potentially break or interact with other molecules, number one, the species that helps this bond break has to supply electrons. Those electrons must be coming in from outside. Not only are those electrons coming in from the outside, but they will likely be going towards which atom? The carbon. Because the chlorine doesn't have any space to put those electrons. Look at its anti-bonding orbital. It's tiny. The odds that I will ever get an interaction there aren't going to work. Where is the anti-bonding orbital on carbon? It's not a P. That one's a trickier question. Where's the bond between carbon and chlorine? We're to draw that in dark green. There's our carbon. There's our chlorine. Where's the bond? Between them. Where's the anti-bond orbital that I want to overlap with? On the outside? So I could go over here. That's outside. Where's that orbital? The complete opposite of the bond, which means the electrons that I supply to break this bond need to come in and react with this molecule on the complete backside of the carbon-chlorine bond. Is that what actually happens? Yes. Shocking. All from just a bunch of little random pictures of balloons. Right? So it's looking at those probabilities. That allows us to predict a lot of information about how we can make and break bonds. Okay? Super, super important. If you don't want to understand where it's coming from, guess what your next option is? What about your mind? Because this is thinking about it. You get to memorize. You get to memorize the crap out of all those possible answers, which you will likely do. Okay? Okay? Which brings us to the next fun part, which is a little mind-numbing for at least me, but it breaks it down. Hopefully you had a chance to watch the nomenclature videos. Okay? I had hoped to put in a few more slides here of nice summary, but I couldn't find them as quickly as I had hoped, and we had to get started with the lecture. Okay? So what's in a name? And what we've got up top is everything that could possibly go into a name. Okay? We have a numbered location followed by the amount of that individual substituent, followed by the name of the substituent. Okay? And then I would repeat that for every new substituent at every new location. And I have to specify the location for every single one of those. Okay? I can get some information about the shape of the molecule sometimes. Okay? I can get the number of carbons specified in the name. I can even get information about the hybridization. Okay? And then the numbered location and functional group, okay, or higher order functional group for an individual molecule. So the point within this slide is to go through and show those connections and then color code them back to our individual drawings. Okay? Maybe a dicey question to ask, but I'm asking anyway. How many people at least read or watched some part of the nomenclature videos? That isn't too bad. Okay? If you haven't yet, you should probably start working on that. So let's take a look at that first one. Let's break that down. Okay? And note, a big issue here, each of those names is officially wrong. We want to know why and how we would fix it. So let's take a look at the first one. How do I start? Well, I start with the hex. Right in the middle of the name. That makes a lot of sense. Right? Because it's so much easier to start in the middle and work your way outwards. Right, what does the hex mean? 6. Because this is organic chemistry, that means 6 carbons. Okay? Before I get too excited about drawing a structure, I want to look for that shape moniker. Okay? Do we see anything about the shape in there? No. So what does that mean? I don't need to worry about it. It's just a chain. I can just draw them out. 1, 2, 3, 4, 5, 6. Okay? We had to be a little bit careful there. In that drawing, what have I already assumed? Single bonds, which was actually the ane ending. Those are all sigmas. So my carbon chain is all backed up by single bonds all the way through. Okay? What's the next piece I can move into? I would argue that I should go with the methyl. And methyl means?
1 ester.
1 carbon. Okay. Which I could show as a CH3. Okay. What does the di in front of that methyl mean? There's 2. So it's not just 1 CH3. There are 2 CH3s. So why did we not call it ethyl? Ethyl means those two are connected to each other. Okay? They're not connected. They are 2 individual methyl groups. Okay? The next part is the location. They're located at which position? At number 3. Where is number 3 on my carbon chain? Okay, now too many people shouted it out. 1, 2, 3, right? Or 1, 2, 3. 2 different directions I could have numbered this to get those methyl groups located. Is there a difference between them? No. So the fun analogy I like to give would be, what is my name? Mike, thank you. In theory, it doesn't change. Let's see what happens. What is my name now? Okay. Just because I turn doesn't mean my name changes, theoretically. Okay. I guess it depends how far away my back is turned. Okay. So we could now draw on those CH3s. Here's where we have an issue with this. The number location must be specified for every single substituent. How many substituents do I have? 2. How many numbered locuses did I give? 1. Which means the name is wrong. How do I fix the name? I would have to specify 3, 3 if I wanted that answer. Make sense? Okay. So guess what? Yeah. Except do it again on your own. 3-dimethylcyclohexane. Where should we start? Hex, meaning 6 carbons. Before I get too excited, I need to look for shape. Do I have a shape information? Yes. Okay. What if it did not give me that shape information? Draw it as a chain. Since it has given you that shape information, what do we have to do? Draw it like a cycle. What things are cyclic? Circles. So let's make it kind of circlish. And we end up with a cyclohexagon. A hexagon. Also known as just a hexagon. So we now have a hexagon. Okay? Why did I draw those all as single bonds? It says ane. Okay? Now what do I have? I have that methyl, which means I have a CH3. How many CH3s do I have? I have 2 of them. Where are they located? At position 3. Okay, so I heard 1's at 3. There's an interesting issue with this. Okay, we weren't super clear, so first mistake with the name.
Not all the substituents are numbered.
I haven't labeled the substituents. So let's go through and make the same assumption we made with the last one. It should have been 3,3-dimethylcyclohexane. Where's position 3? Depends on where I number. It all depends on where I start. So where do I start? Okay. Where is my right hand? It's above me. It's still above me? Is it still above me? No. Does the location of an atom drawn on the page mean anything? No. Where is position 1 on this ring? Wherever I want it to be. Okay? Which is an interesting dilemma. That means position 3 is wherever I want it to be. So if I was to draw on my 2 methyl groups, now let's think about the reverse. Let's name the compound. I would still start with the 6 as our main chain. We have 6 carbons, so hex I agree with. Cyclo I agree with. Ane I agree with. All of those are good. So cyclohexane. Dimethyl. There are 2 methyl groups. I completely agree with that as well. Where are those methyl groups located?
On any carbon.
Okay, interesting. They can be on any carbon. Okay, so given a choice, where are you going to place them? Probably the easiest identifier possible, which would be 1. When we have a ring, guess what? The first substituent goes at what position? 1. If that is always the case, if both those methyl groups, so the first substituent is located at position 1, which means the next one is located, I can't change the structure. The next methyl is located at what position? Still 1. So the name should actually be 1,1-dimethylcyclohexane. The 3's are a copy-paste error, quite frankly. Okay. If they are being defined at location 1 to start, then it is a definition. And if it is a definition, what can we do? We can imply it outright, and we end up with dimethylcyclohexane. I don't need to specify those extra ones. Okay? So, the name officially, dimethylcyclohexane versus 3-dimethylcyclohexane. When it was drawn 3-dimethylcyclohexane, did everybody get that answer? Okay. When it was 3,3-dimethylcyclohexane, did everybody get that answer? When it was 1,1, when it was just dimethyl. Interesting. We came up with 1, 2, 3, 4 different names that all got us to the exact same structure. Of those 4, which one is correct? Only one. All the other 3 are all technically wrong. Even if you can get to the structure from the name, if the name had some flaw in how it was put together, it's still not correct. You can call me, hey, you, and if I respond, yeah, you've got the acknowledgement that you needed. That doesn't all of a sudden mean my name is hey, you. Okay? Yes?
So on a test, do we need a label the one?
Need versus want is a different thing. Do you want to go through? Do you want to go through and number? Probably, because if you don't number it, you will likely draw the structure wrong. By putting in the numbers, that helps you identify where it's going, which brings up a fun question. We came up with 4 possible names for this, and all 4 potentially worked. Okay? Do all 4 deserve equal credit? No. Do all 4 deserve some partial credit?
Yes.
How much partial credit? Okay. Grading nomenclature is the worst job on the planet. Okay? Because what goes into that? Did you put in a comma? Did you put a space between the 3's? Did you put a space between the comma and the 3? Did you put a space between the 3 and the dash? Did you put a space between the methyl and the cyclo? Okay? All of those, by including a space, not including a comma, shifting a dash around, makes the name wrong. Okay? Which means it is a beast to grade on an exam. The easy shortcut that instructors that are intelligent enough to realize that they don't want to have to grade these by hand do what? Multiple choice. All of your nomenclature will be multiple choice. Okay? That does not make it easy, because noticing where those spaces and commas and all of that come into play is a difficult thing to process. But that's now going to be on you, not on me. Yeah. Okay? So you will be expected to go from the name to the structure and structure to the name. Usually name to structure is straightforward because all the pieces are there. It's just a question of interpreting it. The structure to the name becomes a little bit more tedious. Okay? Shall we take a look at the next one? Yes?
So which one was the correct one? Was it 1 or the one without?
Get rid of the ones. Dimethylcyclohexane. You don't want the one because it's implied.
So we're putting the 1, 1, 0?
Technically, yes. This is why I hate nomenclature. Okay. So, it doesn't give you information. If it doesn't give you information, don't include it. Okay? So let's move to the last one. I can tell you guys all love this as much as I do. It's fun. 3-dimethyl hexantuol. Where do we start? Hex. Before we get too excited, no shape information, which means chain. What's wrong with that? Nothing. Why did you not draw it that way? What's that? You don't want to get technically crazy with it when you're drawing it out. Fair enough. But in a multiple choice where you're expected to go from the name to the structure, what can happen with the structure? It can look all crazy. What happened between this versus what you drew as a hex? A sigma bond rotation. Are you responsible for knowing the sigma bonds are allowed to freely rotate and don't change the structure? Yes. Okay. Remember, that's why I said it was important. Okay. Next part. Hex. We got already dropped the and in because they're all single bonds. Okay, you want to jump to the 2-all? I'm fine with that. What does the 2-all mean? What does all mean? Okay. That means we have an alcohol or an OH located at what position? 2. Where's my 2 position? Wherever I want to start counting. Is it going to become more important to label this one for all the positions?
Yes.
Because there's another substituent. So as soon as you have multiple substituents, excuse me, you should make sure you go through and number. And actually I'm going to backtrack that. I bet most of you started numbering with 1 on the far left, right? Yeah, typically what happens when you see them on a multiple choice test. They number them backwards. Why? Did you just say dick? You can't avoid the recording. It's coming. The OH is located at which position? 2. So since I've got it numbered, I can now draw on that OH. Maybe you didn't. Maybe it was just me internally. Dimethyl, which means I have 2 CH3s located at what position? Again, that stupid copy-paste error. Okay, let's get creative with it. Instead of it saying 3,3, let's call it 1,3. Why? Good question. Let's take a look at it in a second. Let's draw on those methyls. So at position 1, I have a CH3. And at position 3, I have a CH3. I have the structure, right? Matches the name. What's wrong with the name? That green part, the number of carbons, is the number of carbons in my chain. So I need to find the longest carbon chain. If I have a methyl group at position 1, my chain length is no longer 6, it becomes 7, which means this name is technically wrong for that structure. What would the name of my structure supposed to be? Seven carbons, which means hept. They're all single bonds, so I can go with hept. Ane. Okay. I can go with an all, located at what position? What else do I have in the structure? I have a methyl, located where? Position 4. Do I have dimethyl anymore? No. My main chain is now all through here. The only things not circled would be the alcohol and that one methyl. Okay? So it's a question of breaking down your structure, making sure that you're very careful within that approach, and we end up going from our structure to our name. Clear as mud. Okay? The reason why I don't like talking about nomenclature, we've addressed a couple of them. We can have multiple different names all leading to the same structure and being able to get there. That does not make those names correct. Okay? So you have to be very, very specific within your name to make sure that you follow the rules. Okay? Which means to do nomenclature, what do you have to do? You need to have all the rules memorized. If you don't know the rules, you suck at drawing structures. There's no way around it. Okay? The rest of the class, if you don't understand electronegativity but you understand structure, you can fudge your way through to an answer. Okay? You can't do that with nomenclature. You must know the rules. Okay? And it's really straightforward. There's only like 5 or 6 rules. Probably more like 500 or 600 pages of rules. Okay? We covered the basic elements of those rules. If you watched that video on nomenclature, I've summarized those primary rules for you to look at. Okay? Those are going to be the big rules. Anything on that slide, which again, unfortunately, I don't have here, but I can at least give you a pretend image of what it looks like. Okay, I think it has something red in the middle, has some stuff down here, some blue up here, saying 1, 2, 3, 4, meth, eth, pro, but, listing our number of carbons. This one says 1 acids. What does it go down to? 8 ethers, maybe? I don't remember. Lists all of our functional groups with the name of the functional group and what we would change the suffix to. Why is that green thing there? The green thing is not in mine, just so you know. We've got some other rules here that list out what substituents are. Substituents typically get the YL ending. The bottom part is the individual steps you should go through and do to identify a name. Okay? Longest carbon chain, that kind of fun stuff. Okay? Find that slide, memorize it. Okay? The basics on that slide, particularly because nomenclature is multiple choice, will get you to your correct multiple choice answer even though you don't know how to put it all together. For the most part. Okay? Questions about that? Okay. I will try and be a little bit more organized with the nomenclature on Wednesday. So we'll do a little bit more practice with that. I'll show you this fancy slide that has everything on it so you can get that memorized. It's again just following the rules. For the first exam, you're talking about the first nomenclature chapter. I think it's NM1. Okay? The rest of them you don't need to stress about quite yet. Okay. Which moves us pretty cleanly into chapter 4. Butanes, C4H10. Why do I have an S? Draw the structure. Draw the structure for C4H10. Okay, should have been able to draw it by now. How many of you drew this as an answer? Oops. Anybody? Ah, so you're all wrong. Okay, because you didn't draw the butane I wanted. What's the issue with just saying butanes? It's very broad. Okay? We can't just look at a formula C4H10 and assume we know the structural answer. There are multiple possible options that could come out of it. Okay? So we need a way to be able to distinguish those two groups and say one is different than the other. But are they different? They have the exact same formula. So can I really call them different? That gets a bit dicey. Okay. If I drew on, say, just this one, now are all three of those best described as being different? Or is there a better relationship or a relationship between the top two that the bottom one does not share with them? Okay. The top two share a common trait that the bottom one does not have. The top two have an extra carbon, right? And the extra, 3 hydrogens? 2 hydrogens? Okay. So we want to be able to distinguish these. Okay. So we have to define that relationship. And that gets fun. And that was kind of sarcastic. So we have 3 terms that we will start to use, okay, at least within this chapter. We have different, we have identical, and we have isomers. Okay? Different means the molecular formulas are different, so nothing about them is similar. Okay? So propane, in comparison back to those two, is different. Come on, pen. So if I drew on propane, the relationship between those two is different. That says different. And because different is too long, we'll just say diff.
So it's like different.
Okay? So those are different. Identical. The formulas are the same and the structures are superimposable. Okay? Well, do we have anything up here that is identical? No. Okay, well, we'll look at that in just a second. So we're going to leave that example off for the moment. And then isomers. The molecular formulas are the same, and the structures are not superimposable. Right? Do we have isomers up here? Yeah. These two are defined as isomers. That says isomers. Okay? So we want to be able to look at structures and identify these relationships ideally in less than 5 seconds. Okay? Ideally. It takes practice to work with. That practice usually comes from manipulating model kits. Okay? So, if we go all the way back to the origins of our drawing, methane. Okay? We really need to draw a Lewis structure for methane. I will take silence to mean yes. Meth means one carbon. That one carbon has all single bonds, 2 hydrogens to satisfy its octet, and we have methane as a Lewis structure. That Lewis structure we could better draw in the VSEPR model with showing our wedges and our dashes, okay, to show the atoms that are not in the plane. We could go through and show this nice fancy ball and stick model. How many of you can draw that in, I don't know, it's even aimed for less than 5 minutes. Okay? That's probably going to be a bit of a challenge. Or we could go to the space filling model, okay, which is a better model because that actually shows where the atoms occupy space. Okay, any of you draw that reasonably quickly? Okay, no. So we want to come up with a way to represent that relatively quickly. That's the VSEPR model we use. Okay? So we could build a model from this. Okay? And then we can draw the model from every possible angle. And I forgot that I left these. Okay. So there's effectively our methane, right? Single carbon, 4 bonds. Okay? If you drew it the way it's oriented right now, okay, plane of the paper is typically the vertical plane. Where would the wedge and the dash be? Okay, I'm seeing a couple people pointing that way. The one pointing at you is wedged. Okay, but wedged which direction? Is it that way? Ooh, there's an observation. It's down. And is it that direction more? Or is it that direction more? That direction. Which means when we draw it, we want to show our wedge aimed a little bit down from our carbon, and we want to show it going that direction. Okay? We would not attempt to draw this model. Let's see if I can do this as a mirror. Let's see what I can do. We got our carbon. No, that's not working. We got our hydrogen straight up. And then that. Hey, I got that. And then we would not say wedge, hydrogen, dash hydrogen. Why is that a bad structure for what you're looking at? Can this wedge be aimed up here? Well, sure it can, like that. But then what happened to the other bonds? They've shifted. This drawing accurately reflects what we're looking at for a tetrahedral structure. 2 solid lines, a wedge, and a dash. What's the issue with 2 solid lines, a wedge? When are we done? 45. Okay. 2 solid lines, a wedge, and a dash. However, where they are drawn relative to each other is incorrect according to the 3-dimensional model. Which means if you now try and use this structure to do any kind of interpretation, you will likely interpret incorrectly and get the question wrong. So when you draw your structures, what you should be trying to draw is as accurate to the 3-dimensional model as possible. How many of you have worked with 3-dimensional carbon before? Yeah. Okay. That's a problem. You've never worked with it, and yet you're being asked to draw it. This is why you have the model kits. Use the model kits. Okay. That will set up the 3-dimensional model in your mind and give you the opportunity to draw it appropriately. Okay. What if we moved up to ethane? What's our Lewis structure? So this is, again, supposed to be fast. Actually, I'm going to erase that. What's the issue with our ethane-Lewis structure? Our bond angles don't look appropriate. And what I had initially started to draw, you notice I was already starting to draw in the Vesper model. That's because what should you be doing when you start your drawing? You should already be jumping to the Vesper model, not drawing the Lewis structure, which means the wedge will likely be aimed somewhere down and away, and the dash will likely be in the same kind of position. A couple things to watch out for. We have a V and a V. Notice those points always aim at each other. We look at the V between the wedge and the dash and the V between the solid lines. They'll always point at each other. They will never be on top of each other or inside each other. And we now have a representation for the model of ethane. Could we have drawn a different one? Probably is always a good answer when I ask a question like that. Okay. So there's what I drew. Right? Hydrogen's up in the plane of the paper. Is that the only possible orientation? Is that different? What happens if we draw that? We're going to see some different organization of our wedges and dashes. Should we be considering and looking at that? Maybe. Okay. Eventually what we'll get, whoa, no, the image I thought I had didn't show up, is that we can see the overlap between our sp3 orbitals. There's the initial one I drew up. If I rotate, doesn't change, which means the free rotation is allowed, which means notice where the wedges and dashes are. They're located in slightly different locations. If we looked at what's known as the seesaw model, there's another potential orientation of that. Okay? That starts to get towards our classifications. Okay? So here's what we'll end with. Yep, looks like fun. I want to know the relationship between the top two and the relationship between the bottom two. We will start that as a quiz within the first 5 minutes of Wednesday's class. Okay? That's all I want to know. What is the relationship between those two structures? Having a hard time with this? It's interesting that there's office hours between now and next Wednesday. You could always sit down and ask, I don't understand what the heck's going on. And we could work through that together.